connected known as fuse wire. Okay, fusing element is connected known as fuse wire. So fuse is what? It is a simplest and cheapest device used for protecting the electrical circuit against fault conditions. Okay, these are the parts of the fusing element. So the base contacts are fixed to the base, and fusing wire is connected to the fuse carrier. The fuse operation is actually based on the heating effect of the electric current. So when current passes through the fusing element, it gets heated up. So under normal operating condition, when no fault is there in the circuit in which fuse has been connected, the heat developed in the fusing element carrying the normal current is dissipated into the surrounding air, and fuse remains at a temperature below its melting point. So when under normal operating condition, when fuse is connected to the circuit, when normal supply current is flowing through the fuse, heat developed in the fusing element will carry the normal current. Okay, and the heat will be dissipated into the surrounding air, and the fuse remains at a temperature below its melting point. This is the normal operating condition of the fuse. Now, when abnormal condition occurs, that is if fault occurs. So when fault occurs, such as short circuit if short circuit occurs in the circuit in which fuse has been connected, or if overload occurs, then current through the fuse will increase beyond its rated value. The magnitude of the current will increase beyond its rated value, and the heat generated due to this excess current cannot be dissipated. Okay, under normal operating condition, the heat that has been generated into the fusing element, it can be dissipated and fuse will not melt. But whenever fault occurs, fault can be a short circuit condition or an overload condition, then current in the fuse will increase beyond its rated value, and the heat generated due to this excess current, it cannot be dissipated, and fuse element will melt, or in generally we will say fuse has blown out. That's what in generally we use the word. Okay, blown out. So fuse will blow out, and the circuit will be disconnected, and it is protected now because the fuse has blown out. Okay, the time required for the fuse to blow out depends on the magnitude of the excessive current. Okay, how much time the fuse will take to blow out, it will depend on magnitude of the excessive current. Means if the fault current is very high, the time taken for the fuse to blow out will be very less. Okay, and if fault current is less, the time taken to blow out will be more. That's why fuse will always have inverse time current characteristics. Why? Because as the fuse current is varying, the time of operation of the fuse is also varying. So you can see here. So this is also one type of fuse. Usually you might have seen it in RPS in our laboratory, circuits laboratory. This type of fuse you might have seen in our machines laboratory. Okay. So fuse has inverse current characteristics. So as the time increases, the current of operation of the fuse, means the time taken for the fuse to blow out will be reduced. Okay. So if you see here, this is the characteristics of a 60 amperes fuse. This is the characteristics of a 100 amperes fuse. This is the characteristics of a 200 amperes fuse. Okay. So you can see the inverse current with respect to time. And the fuse will be okay, here you can see, here in this diagram you can see. So you can see in this diagram that fuse is consisting of a fusible element, that is this wire. You can see a wire here carefully if you observe. If you want, I can expand this image so that it is not expanding. Okay, no. Okay, you can, if you observe here, you can see a fusing element here. So fuse consists of a fusing element in the form of a metal conductor with a small cross-sectional area. So this is a metal conductor which has very small cross-sectional area. Okay, a case is provided to hold the fusing element. This fuse carrier is the case. Okay, and the material used for fusing element will have a very low melting point, low ohmic loss, high conductivity, low cost, and free from deterioration. Okay, so the element, the this metal conductor which is connected in between these two contacts of the fuse carrier, fusing wire. Okay, fusing wire is nothing but fusible element. It will have low melting point, low ohmic loss, high conductivity, low cost, and it is free from deterioration. Okay, so the most commonly used materials for this as fusing element or fusing wire are can be a lead, tin, copper, zinc, or silver. Okay, in general, in your laboratories, you can see a copper wire or a silver wire. Okay, so if for small currents up to 10 amperes, if I want to interrupt small currents up to 10 amperes, generally tin or an alloy of lead and tin around 37%, the alloy will be consisting of 37% of lead and 63% of tin is used for making the fusing element. So if we want to interrupt currents beyond 10 amperes, we generally prefer copper or silver. Okay, so So generally, if I'm using a copper conductor, okay, as the fusing element, then the copper conductor is used along with a soft, faintly bluish white, lustrous, low melting crystalline metallic element that is malleable and ductile at ordinary temperature. Means copper uh, is tinned. Okay, so tinned copper is copper conductor is tinned means tinning means just providing a varnish like thing above the copper which is malleable and ductile. Okay, so malleable means which can be hammered, and ductile means it can be made of a very thin cross section. Okay, so the main purpose of tinning the copper, I hope you have understood what is meant by, means a white, bluish white coating is provided above the copper conductor, okay, so that it can be protected from oxidation. In simple words, if you want me to say, okay. So generally, you can even use zinc in the form of strips as fusing element, okay. If I want the time taken for the fuse to blow out for a longer after a longer period of time, means if fault occurs, and if I want the fuse to blow with a time lag, means if the time taken for the fuse to melt should be more than what if more than in general the time taken for the fuse to blow out while when I'm using another fusing elements. Okay, so whenever we want to have a time lag, uh, then for as fusing element, zinc is preferred. Okay, so which will not blow out or melt for very small overloads. Okay, it won't blow out quickly. That's the reason. Okay, so zinc is used as fusing element in the cases where we don't want the fuse to blow out very quickly. Okay, so when compared to other materials, the time taken for the fuse to melt when the fusing element is made of zinc is very long. Okay, you can see I am not showing you images. There are many images here. You can see these are all the fusing elements, fusing wires. See, this is a fusing wire. This is a fusing wire. In these are three types of. Of course, they are not the actual types in general. They are the fuses. Okay. Now let us see the advantages of using the fuse. So it is the cheapest form of protective device available in the market. That's why better to, means if I want the cheapest protective device, better to use fuse. Okay, so there is no need of any maintenance. Okay, and it can operate automatically. Okay, and for automatic operation, it won't require any elaborate equipment, such as, for example, if I want a circuit breaker uh, as the protective device, then it requires elaborate equipments for automatic operation. But fuse does not require any elaborate equipments for automatic operation. Okay, it can break heavy short circuit currents without any noise or smoke. Okay, so it is available in smaller size. Okay, so and inverse time, it has inverse time characteristics, which makes it suitable for overcurrent protection, and the time of operation can be made as short as possible than that of circuit breaker. Okay, so means if heavy faults occur, so the time of operation, the time taken by the fuse to melt should be as low as possible. Okay, so the disadvantages of using these fusing elements are the time is lost in rewiring and replacing, isn't it? So whenever fuse blows out, you have to manually replace it. So it's a wastage of time. Okay, so if heavy short circuit conditions occur, then fuse may fail to operate properly. Okay, so even if fuse is there, if the short circuit current is very heavy, then it won't be able to restrict that fault to enter into the circuit to which it has been connected. Okay, the current time characteristics of the fuse cannot always be correlated with that of the protective apparatus. Okay, these are all the disadvantages. Function of the fuse, you already know, it carries normal current without overheating under normal operating condition, and under abnormal condition it will break the circuit when current exceeds the rated value. Okay, this is the function of the fuse. Okay, next, characteristics of the fuse element. Okay, so fusing element, it will have low melting point. Okay, so the elements which have low melting point, the fusing elements which have low melting point are tin and lead, and fusing element will have high conductivity, such as examples are silver and copper. And the fusing element, it should be free from deterioration due to oxidation. For example, best fusing element which is free from deterioration and due to oxidation is silver. And the fusing element should have low cost. So lead, tin and copper are available at low cost. Okay, so if you observe here, tin, lead, silver, copper, all are fusing elements actually. But tin and lead has the low melting point, silver and copper have high conductivity, silver is free from deterioration due to oxidation, and lead, tin and copper have low cost. Means all the features, okay, all these characteristics are not available in a single fusing element. Okay, so that's what I have written here. If you see, the above examples reveals that no material possesses all the characteristics. Okay, let us see the terms that are used in the analysis of fuses. Okay, so one of the term that is used for the analysis of fuses is current rating of the fusing element. Okay, current rating of the fusing element. Definitely, depending on the circuit which is to be protected by this fuse. Okay, depending on the rating of that circuit, the fuse rating has to be varied. Okay, so the fuse rating will vary depending on the rating of the circuit. So the current rating of the fusing element will definitely vary. Okay, so current rating of a fusing element is nothing but the RMS value of the current which the fuse element can normally carry without overheating or melting. Okay, so the RMS value of current which the fusing element can carry without overheating or melting is known as current rating of the fusing element. So it always depends upon temperature rise of the contacts of the fuse holder, which type of fusing material that I am using, and the surrounding of the fuse. Okay, so current rating must be decided depending on the temperature rise of the contacts of the fuse holder, which type of fusing material I am using, and surrounding of the fuse. Of course, the primary thing that is to be considered is the circuit to which the fuse has to be connected. Why? Because if the circuit is the means it's the circuit in which normally high currents flow, the rating of the fusing should also be high. Okay, fusing current. So it is the minimum current at which fusing element melts. Okay, so at certain temperature, okay, at certain temperature, so if the current, fault current is flowing in the circuit, okay, so or in the fusing element, okay, so if that fault current exceeds certain value, okay, the fuse will melt. So the minimum current at which fusing element melts, okay, fault current, minimum current is nothing but the fault current. So minimum fault current, I can say the minimum fault current at which the fusing element melts is known as fusing current. Okay, and definitely the value of this fusing current will be always greater than the current rating of that fusing element. Okay, and if generally, the cross section in general, the cross section of the fusing material will be round. Okay, cross section will be round. So wires will be of rounder cross section. So if I consider a round wire, if I is the current, which is it is the fusing current, and d is the diameter of the wire, then I is equal to k into d to the power of 3 by 2. So I can calculate the fusing current depending on the diameter of the wire along with the fusing constant. So this fusing constant value will depend on metal of which of the fuse is made. Metal with which the fuse element is made. Okay, so the fuse constant will always depend on the metal with which the fuse element is made up of. Okay, so the fuse current depends on various factors. One of the factor is material of the fusing element. Okay, fuse current will depend on material of the fusing element. It will depend on the length of the fusing element. Okay, if the length of the fusing element is small, it can easily take away the heat that is produced within the fusing element while current is flowing in it. Okay, and fusing current, this yeah, the fusing current will also depend on the diameter of the fusing element. It will also depend on the size and location of the terminals. It will also depend on the previous history of the fusing fuse. Okay, it also depends on the which type of enclosure is used in which the fusing element is placed. Okay, so these are all the factors are to be considered for fusing current, for deciding the fusing current. Next, fusing factor. Okay, so fusing factor is the ratio of minimum fusing current by current rating of the fuse. Sir, okay, fusing factor is the ratio of minimum fusing current by current rating of the fuse. Okay, you know what is meant by minimum fusing current? Minimum fusing current is the current at which the minimum current at which fuse will blow out. Okay, fuse will melt. Okay, so minimum fusing current by current rating of the fuse. The current rating of the fuse means the rated current of the fuse up to which the fuse will not blow out. Okay, so that the ratio of these two is nothing but fusing factor. Its value will be always more than 1. Okay, smaller the fusing factor value, greater is the difficulty in avoiding deterioration due to the overheating and oxidation at the rated carrying current. Okay, so its value will be always more than 1. Next, for a semi-enclosed or rewirable fuse which employs copper wire as the fusing element, the fusing factor will be usually 2. Okay, so for a semi-enclosed or rewirable fuse, the fusing factor for a copper wire will be always 2. So it is this values are specified depending on the analysis, means based on the study. Okay. So next is prospective current. So prospective current is the RMS value of the first loop of the fault current obtained if the fuse is replaced by an ordinary conductor of negligible resistance. Okay, so it is the first loop, RMS value of the first loop of the fault current obtained if the fuse is replaced by an ordinary conductor of negligible resistance. Okay. Let us discuss more about this prospective current and the first loop of the fault current. Okay. So let us assume in a circuit fusing element is connected. Once again. So let us assume in a circuit to be protected, fusing element is connected and some short circuit fault has occurred in that circuit. Okay. So now when short circuit has occurred, definitely a fault current will flow through that circuit. Okay. So when a fault current flows through that circuit, the fault current may not have symmetry. Okay, since it is an AC circuit, if you see, you can see an AC fault current. This is the fault current, which has a larger first loop. Okay, and a very small second loop. Okay, it is not having any symmetry. So if we can't specifically we can't means faults are unpredictable. Okay, so we can't specify the shape of the fault current. Okay, so it may not have symmetrical shape. Okay, and the first loop of the fault current may be very large. Okay, and this first loop of the fault current will generate sufficient energy to melt the fusible element well before the peak of the first loop is reached. Okay, so this is the peak. This is the first loop of the fault current. You can see here. This is the first loop of the fault current. Okay, this is the peak of the fault current. Okay, and this fault current may has a it can generate sufficient energy. Okay, this fault current can generate sufficient energy to melt the fusible element well before the peak of the first loop is reached. Okay, so the RMS value of the first loop of the fault current is known as prospective current. I hope now you might have understood the definition of prospective current. What is the definition of prospective current? Is that the RMS value of the first loop of the fault current. Okay, so this is the fault current, first loop fault current. You can see here. Okay, so the RMS value of the first loop of the fault current is nothing but prospective current. Okay, so now let us see all the terms in this image. Let us discuss one by one. Let us first discuss about the cutoff current. Okay, so you can see here cutoff current. I have mentioned here this point A. Okay, so it is the maximum value of fault current actually reaching before the fuse melts. Okay, so before the fuse melts, the maximum value of fault current that actually reached before the fuse melts. Okay, on the occurrence of fault, means when fault occurs, the fault current has very large first loop due to the fair degree of asymmetry. Okay, so because of the fair degree of asymmetry, what is happening is the fault current has a very large first loop. Okay, and whatever heat is generated due to this very large first loop of the fault current, it is sufficient enough to melt the fuse as soon as the fault current reaches to point A. See, initially the fault current has started from this instant. You can see I have written here fault occurs. Okay, from this instant, fault has occurred at this instant. The fault current is gradually increasing. Okay, fault current is gradually increasing. As the fault current is increasing, the temperature of the fusing element is also gradually increasing. Okay, the temperature of the fusing element is also gradually increasing. As soon as it reaches point A, the fusing element will reach to its melting point. Okay, the fusing element will reach to its melting point and the fuse will blow out. Okay, and the current at this point, okay, the current at this point here, you will call it as cutoff current. Okay, so the cutoff value will depend upon current rating of the fuse, value of the prospective current, and asymmetry of the short circuit current. Okay, so this cutoff current will depend on three factors. One is current rating of the fuse. Okay, so what is the rating of the fuse? Okay, so if the rating of the fuse is high, okay, the time taken for the fuse will maybe much more when compared to the, of course, when compared to lower rating fuse. Okay, and it also depends on the value of the prospective current. Now you know what is the definition of prospective current. Okay, and it also depends on how unsymmetrical, okay, how asymmetrical the short circuit current is, means the fault current is. Okay, this is about cutoff current. Next, pre-arc heating time. If you see here, this is the time interval. Okay, so from it is the time interval between the fault occurs, the instant when fault has occurred to the instant when the fuse has melted, means it is the interval between fault occurrence and cutoff current. The interval between fault occurrence and cutoff current is known as pre-arcing time. Okay, so when we know when fault occurs, what will happen? The fault current will rise rapidly and generate heat in the fusing element. Okay, so as the fault current reaches the cutoff value, this cutoff value point A, the fuse element will melt, and what will happen? An arc is struck between the contacts. We generally say use that word in the case of our circuit breakers. Here, okay, so you can see a spark, isn't it? Whenever fuse blows away, you can see a spark. That spark is nothing but the arc. Okay, so I hope many of you might have seen it. Even if you have not seen it, don't worry. We are going to have fusing element characteristics. Okay, fuse characteristics experiment in the power system laboratory. Okay, so I may be the one who is going to conduct the experiment for you people. And in our laboratory, we have 5 amperes and 10 amperes fusing element. And for different lengths of the fuse, for the same cross section, of course, for different ratings, rating fuses are there in our laboratory. Okay, so we are going to study the time taken by the fuse to blow out. We are going to study about it. We are going to do the experiment, and we are going to plot the characteristics, inverse time characteristics. We are going to plot it. Okay, in the laboratory, power system laboratory. You people will be having that laboratory next semester. Okay, so the time between the commencement of the fault current, which tends to cause a break in the fusing element, and the instant of arc initiation. Okay, so as soon as it reaches the point A, what happens? Fuse just blows out. Okay, so fuse will reach to its melting point. Okay, so at this instant, arc is struck. Arc is means, of course, it will. You can see a spark there. That spark will exist for very less second. Means it may be around microseconds. You can't even. Within a glance, it will just go. It will go off. That's all. Okay. So the time interval between fault occurrence and cutoff current is nothing but pre-arcing time. In technical words, if you want me to say, it is the time between the commencement of fault current, which tends to cause a break in fusing element, and the instant of arc is initiated, is known as pre-arcing time. So this at instant A, okay, at point A, the arc will be struck between the contacts of the fuse. Okay, arc is initiated. Okay, arc is initiated. Okay, now let us discuss about this arcing time. So how arc is initiated, how arc continues for a very short duration of time, how arc persists. Okay, so arc emission and continuation we are going to discuss in detail within this unit in the next chapter. Okay, arcing phenomena. Okay, arc extinction phenomena and all we are going to discuss in detail in this unit only in the next chapter. Okay, next time arcing time. So this is the time between the end of the pre-arcing time and the instant when the arc is extinguished. So at this instant, at point A, the time at this instant, what is it you can say? Just pre-arcing time ends here. Okay, pre-arcing time will end at point A. Okay, so the time interval between, if you see here, arc has initiated here, but the current is gradually reducing till this instant. Okay, at this instant, what is happening? The fault current is becoming 0. Means arc has struck between the contacts of the fuse and it has gone away. Okay, so for a fraction of second, you can see the arc. Okay, and it just within fraction of seconds, it just goes away. So arc has initiated at this point A, and it has means arc current becomes 0 at this instant. Okay, you can see here I have written current 0, so arc finishes. Okay, so of course fuse has blown out at point A and arc is struck. That arc will persist for very short duration of time. We can't even recognize it with our naked eyes. Okay, so that interval is known as arcing time. So this is the time between end of the pre-arcing time and the instant when arc is extinguished. Okay. Next is total operating time. Okay. Total operating time, it is the sum of pre-arcing time plus arcing time. Okay. So at instant A, what happens? At instant A, what happens? Arc is struck. Okay. Arc is struck between the contacts of the fusing of the fuse. Okay. And it will just extinguish at some other instant. Some instant. I have not given your notations. Otherwise, I might have used those notations here. Okay. So total operating time is the pre-arcing time plus arcing time. Okay. Now, actually, what is the purpose of this? What is the purpose of this fuse? It has to break the fault current. Means it has to extinguish the fault. It has to interrupt the fault current. Okay. So each fusing element will have its own breaking capacity. Okay. Each fusing element will have its own breaking capacity. So the RMS value of AC component of maximum prospective current that a fuse can deal with at a rated service voltage is known as breaking capacity. So the breaking capacity means fault current interrupting capacity. Breaking capacity means fault current interrupting capacity of the fusing element will vary based on its rating, based on the circuit to which it has been connected, and based on the magnitude of the fault current. Okay, the breaking capacity of the fuse will vary. So breaking capacity can be defined as the RMS value of the AC component of the maximum prospective current that a fuse can deal with at rated service voltage. Okay. So, okay, this is about the fuse. Okay, and different terms that are used in the fuse. And I will continue. Okay.